All right. Oh. Okay. Good morning. How are you?
I'm good. How are you?
This is fine. I'm still getting my stuff set up, so pardon me for tapping away here. Oh. Okay, good morning, everybody. Okay, time to get started. So welcome, everybody. I hope everybody had a restful weekend. Let's see, let's dive right in. Here's, by the way, before we get into the math, I guess I'll point out that here's our lecture schedule, and you can see we're already a little behind. This is routinely the case in my classes, and it always works out. I do always catch up, so nothing to worry about. But behind in the sense that we were supposed to have finished section 1.4 on Friday, and of course we barely started section 1.4. Okay, so anyway, no problem. We're gonna get there. Okay, so here's what we were doing. We were talking about the cross product, and well, we were building up to the cross product. So let me remind you, we talked about different ways of describing orders of lists of vectors. So specifically, if you have two vectors in R2, then we pretty much talk about counterclockwise and clockwise, and of course, dependent is neither, and exceptional. And this is geometrically natural. These two orderings are mirror images of each other. If you trade the positions of the two vectors, you switch the order, and etc. This is one I think is underappreciated, is that it's independent of rotations. As long as you rotate both the same way, same amount, this is preserved. So, okay. All right, and then analogously for three vectors. Now, this one's a little bit less sort of like, familiar, but there's this idea of right-handedness and left-handedness. And so specifically, quick reminder, the first vector in the list, use the index finger of your right hand parallel to your palm to point in the direction of that vector. The second vector on the list, you use your middle finger, bending it the way middle fingers want to bend. And then having done whatever it is you have to do to get those two fingers, following those rules in the direction of the first two vectors, they define a plane. Your thumb is on a well-defined side of that plane. And if the third vector given is on the same side as your thumb, then that's a right-handed list. Otherwise, play the same game with your left hand. You'll find your thumbs go the other way. This is a good exercise. Think this through, right? Then it's a left-handed list. Okay. All right. And again, mirror images, trading changes the order, independent of rotations. And then there's a new one to talk about, and that's this idea of cycling. And again, just, trying to be quick here. If everything moves over and then whatever would have fallen off the side goes back around to the other side, that preserves order. Okay. All right. So, okay, so here, that's where we left off last time. So I want to talk now about some theorems that y'all have presumably seen in Math 218. And these, well, I'll start with the first one, go back to 2 dimensions, and assume we have an ordered list of 2 vectors in R2. And out of that list, we're going to make 3 things. On the one hand, we're going to make a matrix. You're just going to take these and make them the columns. Next, we're going to make the linear transformation. And of course, whenever you have a matrix, you have a linear transformation, right? I mean, so given a matrix, this is a function. That function is linear. So linear transformation. And then thirdly, we're going to make this parallelogram. It's the parallelogram which has edge vectors that are A and B. And so you can just sort of, again, directly out of these 2 vectors, A and B, make that parallelogram. I'll point out here as well that it is the image of the unit square. If you were to consider the unit square here, right, and look at all the points there and see what comes out of, when you plug into the linear transformation, what comes out, well, you get the exact same parallelogram. Okay. All right. So with those 3 things made, here's the news. Here's the information. The determinant of this matrix is equal to the area of that parallelogram. That's the first one. And I misstated that a little bit. The absolute value of the determinant, that is important. It is the absolute value. Determinants are allowed to be negative, right? Determinants are about half the time are negative. And area, of course, is an intrinsically positive concept. Okay. All right, so that's the first fact. The second thing I want to point out is that this determinant, not its magnitude, but its sign, whether it's plus or minus, tells you 2 things. On the one hand, it tells you about the order. It tells you whether that's clockwise or counterclockwise. Let's see here, clockwise or counterclockwise. And it also tells you something about this linear transformation. It tells you about whether the transformation is, flipping the plane upside down in some sense, inverting things or not. Okay, and specifically the way it tells you these things is by way of these rules, and it's just a lot to write down. So positive determinant means that the list is counterclockwise and no inversion happens and all orders are preserved. So determinant positive is kind of the good news. It's kind of the nothing bad happened. Everything's normal. Everything's as would be expected. And on the other hand, if determinant's negative, it's a clockwise ordering. And the plane is kind of, in some sense, kind of flipped or, turned inside out, inverted, however you want to say it. And all orders are reversed. And you can kind of see a version of that. Let me draw a picture here. Let's suppose that our picture isn't this, but let's suppose that our picture is like, let's see here. So let's suppose that our first vector is like that. And don't forget, our first vector is the image of the first standard basis vector, E1. And then let's suppose that our second vector is like that, that being, of course, the image of our second standard basis vector. And you can kind of see the flipping, inverting, whatever you want to call it, in happening here, because while green to blue, namely the order given, is counterclockwise before the transformation, it's clockwise after the transformation. Right. And so, how did that happen? Well, that's maybe a lot of things happened. Maybe there were stretches and shears and who knows what, but at some point something flipped. Right. Okay. All right. So again, I hope this is a reminder review from Math 218 linear algebra class. And of course, there's a third possibility. It could be the determinant 0. Now, if the determinant 0, this is kind of the anomalous case, and it means something's bad. So in particular, it means that these two vectors, they're neither counterclockwise nor clockwise, and therefore they're dependent. And if they're dependent, then that means that, well, either they're parallel or one of them 0, something like that, and the plane is squished. So it's the something's gone terribly wrong possibility. Okay. All righty. And there's a three-dimensional version. Again, I hope this is something that will be familiar. I deliberately wrote this next theorem on the page, very much, sort of laid out on the page in the exact same way as much as I could as the previous theorem, because they're really, really similar theorems. They're basically the same theorem, just in 3 space instead of 2. And so if you have, again, a list, but now a list of 3 vectors in R3, then, well, again, you can make a matrix by making those vectors the columns, right? Whatever the order of the list is, that's the order in the columns. You can, of course, given any matrix, you can make a function, which is, of course, linear, thus a linear transformation. And of course, then you can also take those vectors and make a box, parallelepiped. Okay, and then you get basically the same results. The determinant tells you the volume, again, with the absolute value. And the sign of the determinant tells you about, in some sense, whether this, where is everything right or is everything inverted, right? So positive means the vectors are in right-hand order and nothing got inverted and everything's preserved. Negative means that the list is in left-hand order and yep, there was an inversion and all orders are reversed and everything's backwards. You're in mirror world, right? Well, anyway. And then, of course, there's the anomalous, the determinant could be 0, in which case the vectors are dependent and everything's squished in and everything's haywire. Okay. So again, reminder, and let's see, I'm going to have to think about how to write this now. If we make our first standard basis vector there, second standard basis vector is like that, third standard basis vector is like that. So blue, green, orange, purple, blue, green, purple as that's first, second, and third. Well, the way I have this drawn here, A being the image of the first standard basis vector, B being second column, image of the second standard basis vector, and C, third column, image of the third standard basis vector. You can see that this right-hand listing that we had here, right? First standard basis vector, second standard basis vector, third standard basis vector. They're always a right-hand. That's all. That is a right-hand order. The image there, let's see if I can do this about right. Something like, oh, wait a second. No, see, I'm trying to see how this is going to look for y'all. Gosh, it's slightly to the, okay, so my right is it's going to be your right. That's my left. Something like that, I think. Right. And so, yeah, right-hand order turned into a right-hand order. And so that was the way I have this drawn here. This corresponds to a positive determinant for this matrix.
Could you explain what a standard basis vector is?
Oh, yeah. Standard basis vectors are just E1, E2, E3, or IJK. You might have seen them as IJK, but it's just the unit vector pointing in the X direction is the first standard basis vector. Unit vector pointing in the Y direction is the second, and then Z direction is the third. Yeah. Is that cool?
Yeah, so then how did you get those from the columns of the matrix A?
Oh, yeah. Well, so if you multiply, let's just actually multiply one out here. Let's do the second one, just arbitrarily. If I were to multiply this matrix by 0, 1, 0, which is, of course, the second standard basis vector. Well, you multiply that out and, well, you get the second column. Yeah. So in the sense of this function, multiplying by vectors to get other vectors, this green vector here, and let me highlight with the yellow. This vector here, its image is that vector there, which is that. Good. Okay, so I hope this theorem looks familiar. Again, this should have been covered in Math 218. And let's see here. Yeah, okay, so with that down, I'm going to now define the cross product, finally. I do want to note, and this is important, that the way I'm defining cross product is different from the way the book defines it. It is equivalent. So it's not, in terms of how you're going to, what you're going to compute, how you're computing it, the results, what's true. It said the book and I are 100% in agreement on that. That's not a dispute. But, what we choose to make as the definition, the book and I don't see the same on that. So I'm going to define it a little bit differently, come to all exact same conclusions. Okay, so here we go. Here's my definition of the cross product. I'm just going to write the formula. There it is. That's the formula for the cross product. So definition. Nice and simple, just a formula, right? And now this formula, it turns out, has a lot of neat properties. And what's going to be one thing that's going to be really convenient about proving those properties is I've got a formula with which to prove them. The book's choice. If you look at the definition of cross product in the book, they define the cross product as the unique vector with certain properties. And then you're like, how do I know that this vector even exists? How do I know there aren't multiple of these vectors? It's I don't know. It's a little bit unsettling. So, but it's perfectly reasonable. Okay, so there's our definition. Now I'm going to point out, I think this is worth noticing, this is a valuable observation actually, is that this formula you can think of as being this, what I call symbolic determinant, pretty standard term. And what we mean by a symbolic determinant is that ignore the fact that this is not really a matrix. Pretend that it's a matrix temporarily, and just compute as if, compute determinant as if it really was a matrix, and whatever you get, that's what I'm talking about. So it's called a symbolic determinant. And I say this isn't really a matrix, at least it's not a matrix in the usual sense, because a matrix is supposed to have elements that are numbers. All of those are numbers, but then up here, that is not a number. That's a vector. And having a vector as an element of a matrix is, that's weird, right? That doesn't seem right. So sure, right? Confession, it doesn't seem right. Let's let that slide because it's very convenient. Okay. All right, so now is this really what I claim it is? Let's compute and see, is the first element what it's supposed to be? Here, let me do it like this. The first element, there it is. Well, how would I compute the first element from this symbolic determinant? The first element would be, well, what gets multiplied by E1? Well, what does get multiplied by E1? Well, A2B3 minus A3B2. Exactly what we have there. Right. And then likewise, I mean, the different component, the second component, third component. Well, yeah, you just kind of go right along. And don't forget, when you're computing determinants, you have this whole plus minus plus, and you can see that the corresponding negative sign is right there where it should be. So, I mean, if you just kind of write it all down, this works. Okay. All right. Now, here's a similar observation. This one feels a little weirder, but really useful fact. Let's toy with how to compute that dot product with the cross product. It's not clear why we'd be interested in such a thing as we start this process, but it turns out it's really useful. So, okay, there it is. There's my first vector, and I'm dotting with, well, the cross product, which of course is right there. So I'm just kind of recopying, and well, how do I compute this dot product? This dot product, I take that, which, oh, by the way, is there. And I then multiply by this thing, which, by the way, is that times that minus that times that. Right. And then I keep going and adding. So it's the determinant again. It's a determinant of a very similar looking matrix. This one's an actual matrix. I mean, all those elements are numbers, as they should be. So sure enough, now a little kind of a weird observation there, but what we get is that this construction, a dot product with a cross product, is a determinant. So how is that useful? Why is that useful? It turns out this is a phenomenally useful fact because here's the thing. We already understand dot products pretty well. We understand determinants. I mean, pretty well, right? I mean, we know a lot of facts about determinants and volumes and right-hand orders and, stuff like that. So now we have an equation here that relates two things that I understand pretty well with the cross product, which I don't understand very well yet, but I want to. And so this is going to be our foot in the door. We're going to use what we know about dot products and determinants and this equation that we just observed. And from that, we're going to be able to draw conclusions about cross products. So, all right. Okay, so let's see how that plays out. So here's our first example. I claim theorem, the cross product is orthogonal to both A and B. That's a neat fact. Now, how do you prove that? Well, orthogonality is easy. Orthogonality means that the dot product is 0. So let's compute these dot products. I just need to confirm that we get 0 out of those dot products. And if you want to brute force it, you can, right? We have formulas for the cross product. You could just crank that out. But even better, check this out. Because I'm doing a dot product, for example, with a cross product, I can say, hey, that's that triple product thing from above. This being a triple product is a determinant. That's the algebra that we just saw. And determinant, I know things about, right? So specifically, this determinant, being a determinant, its magnitude is a volume. It's the volume of the parallelepiped that I get by taking this first vector, A, this second vector, also A, all right, this third vector, B, and I'm supposed to make the parallelepiped now whose edge vectors are A, and B. And well, two of those vectors are the same vector. This parallelepiped is it's a flat parallelepiped. It's what I like to think of as, already, flattened for recycling, like a cardboard box. right? So, I mean, it's just geometrically a freebie that this volume is 0. And if that volume is 0, well, that means that this triple product is 0. Therefore, this dot product is 0, and that means orthogonal. So this is a slick move, right? This is a really clever little bit of algebra. I wish I thought of this, by the way. I didn't think of this. Somebody showed me this many years ago. And so, no, they didn't think of it either. Somebody showed them. This is a really clever idea that's trickled its way down through the years. And so this observation about triple products is the foot in the door that allows us to use determinant to draw a conclusion about cross products. Well, in fact, determinants and dot products to draw conclusions about cross products. Okay. All right, so it's a nice move. Okay, next cool fact. These 3 triple products are all the same, and it's easy to kind of glance at this and be like, oh, it's another one of these boring, obvious, algebraic formalities that, it's like, oh, the distributivity property or the something like that. But slow down. It's not quite, because the 2 vectors that were involved in the cross product here, it's not like I just moved the dot to the other side or I switched the 2 vectors that were involved in the cross product, one of them pops out and is no longer involved in the cross product. Now it's the thing I'm dotting with. So that's weird. There's nothing algebraically obvious or algebraically expected about this. This is not sort of like, well, of course you would algebraically, I mean, my God, life would be brutal if this wasn't true. No, this is a unexpected, weird fact. So how do I know this is true? A couple different ways you can see this. One is to say, well, that's a determinant of a certain matrix. And that's a determinant of a different matrix. Those matrices have the same 3 rows. They're just in different order. They're just transpositions of rows from each other. And we know what happens when you transpose rows, right? What transposing rows does to determinants, rows or columns, whatever. And in fact, if you count how many transpositions have to happen to turn this one into that one, in fact, it's exactly 2. So you can turn the red matrix into the green matrix by way of 2 transpositions, which gives you 2 minus signs, and therefore nothing happens. So these triple products are the same because the determinants are the same. Okay, let me pause on that for a second. Everybody see the argument? I didn't write out the algebra there. By the way, I am moving kind of fast through this material because this again, a lot of this stuff you should have seen in Math 218.
So is it that they're the same because if you rearrange the rows, the matrices still have the same determinant?
Yeah, well, no, well, so when you transpose 2 rows in a matrix, the determinant gets a minus sign. And the thing is, to turn this one into that one, you'd have to transpose 2 rows and then transpose another 2 rows. So you get 2 minus signs, which of course is 0 minus signs. Yeah. Okay. Now, there's another way you can think about this, more of a geometric way to think about it, and that is to think about this. Well, anyway, so let's think about what are the magnitudes of these 3 numbers. Well, the magnitude of a determinant, keep in mind, they're triple products, but they're therefore determinants. Magnitudes of determinants are volumes. Well, here we have the volume of the parallelepiped whose edges are A, B, and C. And then here we have the volume of the parallelepiped whose edges are A, B, and C, right? And likewise here, it's the exact same parallelepiped 3 times. And of course, the volume is exactly the same. And so therefore, these numbers have have all the same magnitudes. Now, as far as we know, maybe one's plus, one's minus, something like that, right? But they definitely have the same absolute values because they have the same volumes. Now, what about the plus and minus? What do we know about the minus signs? Well, the minus signs are determined by whether this is a right-hand order or a left-hand order, and this by whether it's a right-hand order or a left-hand order, and likewise that one. So what can I say about whether these are right-hand orders or left-hand orders? Well, they're all cycles of each other, right? Each one of these, ABC, is what you get when you cycle BCA, which you get when you cycle CAB. So because they're all cycles, these determinants all have the same signs. I don't know if they're plus or minus, but they're either all plus or all minus. Okay, so these three numbers have the same magnitude and the same sign, therefore they are equal. So kind of a geometric point of view, if you prefer. All right. Now here's one of my favorite little arguments. This is crazy tricky. I did not think of this on my own. This one, I mean, I definitely got, I'm sure I must have been shown this at some point long, long ago. It's a super clever idea. And again, the person who showed me, they didn't think of it either. Somebody showed them, and you trace it back to someone who's super, super clever. So anyway, here's the idea. The theorem that we're going to try to prove says that the magnitude of the cross product is the area of the parallelogram defined by those two vectors. Oh, and by the way, I should note this right here. That's a notation that I think I may be in the process of coining. I think it's really convenient, but rather than say the parallelogram defined by, I just put the two parallel lines. That means parallel of whatever. With two vectors, it means parallelogram. With three vectors, it means parallelepiped. It's just a very handy little shorthand. Okay. So the magnitude of the cross product is the area of the parallelogram. Really cool fact. And we're going to get to why those two quantities are equal by considering a third quantity that we do not immediately see why we would care about. But let's think about that determinant. Again, this is really clever. This is not something that should naturally follow in your minds. Don't expect that you should have come up with this on your own. You shouldn't. But let's think about the expression here, this determinant. Well, on the one hand, determinants are triple products, right? And the way determinants are triple products is you take the first vector and then you dot that with second vector dot third vector. Cross third vector. So that's just a triple product construction. We know determinants are triple products. And then we observe, oh, well, the spacing is different, but it is nevertheless that this is the cross product. Sorry, typo. I just found a typo. By the way, keep in mind, this is my first time teaching this class. These lecture notes are brand new. There's going to be typos in them. This is a typo. Let me do this in red. This, of course, is not a cross. This is a dot. Sorry about that. So yeah, spaced. Okay, I'll get that fixed. By the way, always the case, whatever I have of my lecture notes, the updated version with as many typos as possible fixed and with as many pages as available in it is always in the resources section of our class Sakai, our section Sakai site. And so, download, regularly. But anyway, so this is a typo. I'll get this fixed. I'll have it done by the end of today. Okay. All right. So we have here then triple product, right? Dot product with a cross product. Also, in this case, is a dot product of a vector with itself, which therefore is magnitude squared. Okay. So we have shown that this thing that we don't care about is equal to this thing that we're not sure why we should care about. So yeah, this does not seem that useful yet, but again, bear with me. So what else can I say about this determinant? Well, determinants are volumes, right? So it's the volume of a certain parallelepiped, and specifically the parallelepiped whose edges are the cross product. And then A, and then B, right? So let's cross product A, B. Okay, so it's that volume. Fine. What's this volume? How would I compute this volume? Good news. We already know that this vector. Whoa, gosh, wrong color. This vector here, we already know is orthogonal. We already know that these are right angles. And so because they're perpendicular, what that means is this volume is just that magnitude, namely this distance, right, times this area, right? Because of the right angle, the volume is purple times orange. Okay, so again, why do I care about that? Well, I don't really immediately care about that. Neither one of those things is something I'm immediately interested in. Okay, altogether though, this thing being equal to that, okay, well, yeah, but it's also equal to this. So therefore, this is equal to that. Cancel a common factor, and we get what we wanted. Right, that tells me this.
Can you explain again how you got from the determinant to the triple product?
Yeah, so that's this fact here that determinants are triple products. It's just an algebraic. I mean, it's weird algebra, but it's immediate. It's just noticing it. If you punch up that triple product and if you punch up that determinant, it's the exact same algebra. Is that cool?
So I understand that, but I don't see how it goes to the triple product that you wrote below specifically.
Okay. Yeah. Okay. So when you have a determinant, first row dots with second row cross third row. That's the rule. That's the way in which you get the vectors that participate in the triple product out of the determinant that it's equal to. And so that's all I did here, right? So let's see here, first vector, right? First row, and then let's see, second row and third row. Is that cool? Yeah. So, again, clever, right? Again, I wish I thought of this, but I'm sure someone showed me this at some point, but very, very clever little construction that we take something arbitrary that happens to connect in different ways, and then the answer we're looking for just pops out. So really, really neat.
Do you mind going over that very last step one more time?
Oh, okay. You talking about this right here? Or are you talking about what I just did?
No, from that draw, I followed all the way up to the drawing, except the last canceling part.
Oh, you mean all this stuff down here? Yeah. Are you there?
Yeah.
Okay. So this stuff down here. Okay. Well, so the big idea is that because this is perpendicular to all of this. Right, when you have perpendicular in a three-dimensional shape, then you can take it's basically the volume is the area of the base times the height, right? So the area of the base is the area of the parallelogram, and the height is the magnitude of that cross product vector. Yeah. Okay, if you have any more questions about it, look, we can talk in office hours. Okay. Okay, so yeah, so there's just a bunch more facts that we can show. Neat fact, when the cross product is 0, that means that the pair of vectors is dependent. And this one is actually kind of an immediate consequence of the one above. They both of these statements are equivalent to saying that the area is equal to 0. I mean, if you think about it, the magnitude of the cross product is the area. So if the cross product is 0, then the area is 0, right? But linearly independent would mean that those two vectors are either parallel, in which case the area is 0, or one of the vectors is the 0 vector, in which case the area is 0. They're just the same. So neat that this connects to seemingly otherwise hard to connect ideas. Okay. Another neat little fact. This is what I'm going to loosely call always in right-hand order. And I didn't write it like that because it's always possible that something's 0 and therefore it's, there's a dependence. But in your mind, you can get away with thinking of this as always in right-hand order. To be precise, I'll say it's never in left-hand order, right? And so easy fact to prove, because how would I decide on this order? Well, I'm going to start by computing this determinant. If you want, you can think of it as I'm going to take this and cycle it over to the left side, whatever. But let's think about this determinant. That determinant, as we saw above, same algebra, is a magnitude squared, which is never negative. And so therefore that's never a left-hand order. And then if you know that this is not a left-hand order, then you can take that and move it over there, and therefore that's never left-hand order either. Okay, so real clever move. So many little connections between the various constructions that we have: determinant, dot product, cross product, and their algebras, right, and their geometries. So many different little connections. Okay, so we actually we've now proved all of the facts about cross product that the book takes as the definition. So the book does it a different way. The book takes the geometry as the definition and then proves the formula. I'm starting with the formula and proving the geometry. So it's all equivalent. I think my way is more geometrically satisfying. There's a lot less sort of brutal algebra. And if you take a look at the way the book does it, there's a lot of, you got to slog to to get to those conclusions. So anyway, personal preference. But the definition that the book uses, what I'm going to call a conclusion, is the cross product is the unique vector that has these properties. It's perpendicular to the inputs. Its magnitude is the area. And it's a right-hand ordering. And it's not a left-hand ordering. So there is a unique such vector, and of course we also know the formula for it. It's the formula that we made the definition. Okay. So couple of additional facts that I think are worth pointing out. The cross product, very important to note, is not commutative. A cross B is not B cross A. It's weird. This is one of those things that kind of feels like it ought to be true, right? We're accustomed from high school algebra to feel like, well, times's are supposed to be commutative. This one's not. Of course, y'all have seen matrix multiplication, also not commutative, right? So not your first example. However, even though they're not commutative, this one is, I should say, anti-commutative. So when you switch the orders of the two vectors, you get the exact negative. And it's an easy conclusion. It's just basically if this is A and that's B, right? And there's your cross product. Well, if you switch the order of these two vectors, the cross product just goes down the other way. I mean, it's I think a pretty easy pitch, and it follows immediately from the conclusions we have above. Couple of other facts. This is a combination of observations that the book makes. I think it's easier to kind of combine it into a single statement that cross product with a given fixed vector A is linear. So linear in the sense that this vector here, being the input vector, that's the input to the function. When you take a linear combination of inputs, right, that you're crossing with A, right? That's what our transformation T does, is it crosses with A. Linear combination going in gives you a linear combination coming out. Okay, so that's that linearity. And it works on both sides. So here I have it written as, being on the right. It also works on the left. If you were to rewrite your function T to be cross product with a vector on the right, and therefore input on the left. So still also linear. Okay, and real quick, also not associative. So this is another one of those things that looks like it ought to be true. Okay, high school algebra makes us feel like it ought to be true, but it's not. So heads up about that. Okay, pausing again.
Are x1 and x2 just some random vectors?
Yeah, that's right. So when I say linear, what I mean by linear is that no matter what, this is true for any C1, any X1, X2, any C1, C2. This is true for all of those things. So this is the same notion of linearity as from linear algebra. Yeah. So any vectors and any scalars, this always works. Yeah. Anybody else? Okay. All right. Okay, a couple of quick applications. The book has a neat one in there, which is that torque is actually pretty well described by cross products. So torque, if you have some sort of an axis that things are turning around, and you're applying some sort of a force, and well, how hard is that really going to turn, right? How much are you really going to need to push in order to get that bolt to unstick? Well, the way you can compute that is by taking the vector describing your lever arm and the vector describing the force that you're applying, and that will compute by way of the cross product. Then you get what they call the torque vector, and that represents how much turning power you're applying. And so the cross product is what computes that. Okay, so that's a nice example. And I'll point out another application. This is I don't know, arguably anyway. This is something I see as being really kind of more important. But cross products are how you compute forces of charged particles moving through magnetic fields. So if you're a physics major or a double E major if you're going to be dealing with electric fields and magnetic fields and that kind of thing, anything with E and M, this is a pretty big fact. So the idea is that the amount that the charge is moving, so charge times velocity, cross product with the magnetic field, that cross product computes the force. And so as this particle moves through that magnetic field, the force that it experiences is that cross product vector. Okay. All righty. Why did I erase that? I don't even know why. I'll just leave that there. Okay, so we're going to move along now to equations of planes. This, I believe I understand, is not review from Math 218, or at least not much. You might have seen maybe a little some of this, but I'm going to go ahead and treat it as if you have not seen it before. And I'm going to start by deriving the equation for a plane in space. We have to know something about the plane in order to be able to have a sort of a foot in the door. So I want to talk about the plane that is perpendicular to a given normal vector, what we call a normal vector, and that goes through a given point. So it contains this point and it's perpendicular to this vector. So I think you can see that, if you have a point and a normal vector, right? If it's got to be perpendicular to that normal vector, then you kind of know how the plane is oriented. And then if it's got to go through that point, it's stuck, right? There is only one such plane. Is exactly one such plane. So how would we describe this with an equation? Well, keep in mind, an equation is a test. How would I test some point here? Well, easy observation to make. I claim that point is in the plane if and only if this difference vector is parallel to the plane, right? So here, the point is in the plane. That difference vector is parallel to the plane. If I were to put the point up here where it's not in the plane, then this vector, that difference vector, would not be parallel to the plane. So the way we test these points, a way to test these points is to say, well, it depends on that vector and whether it's parallel to the plane. And then easy observation, parallel to the plane means perpendicular to the normal vector. And we've got ourselves an equation, which you can rewrite, of course, like that. So nice little argument. I think that's persuasive geometry. And this is how we write the equation for the plane. Now, I'll point out, I think this is worth noticing, that if you crank out that dot product, and keep in mind, the coordinates of the x vector, x, y, z, that's the point, that's the point whose position you're testing. If you call the normal vector coordinates a, b, and c, the nice punchline is you can read that backwards. And that is that when you have an equation of this form, right, then these coefficients, they are the coordinates, they are the components of that normal vector. So really cool fact, you can just at a glance at an equation for a plane, you can instantly read off what is the normal vector for that plane. Okay, pausing. How are we doing? Oh, I can't pause. I'm out of time. So we will. Let me draw the line here. That's where we're now done for today. And let's see here. Let me stop the share. Let's see here. I hope everybody had a great weekend. Good to see you. See you on Wednesday. See you later.
Thank you, Professor.
Thanks.
Thank you.
Thank you.
Sure.